will use the small signal equivalent circuit analysis to derive the common mode gain ACM, the differential mode gain of the amplifier AD, and then in terms of these two gains we will have the common mode rejection ratio CMRR of the differential amplifier. So if you look down at the bottom, figure 6 over here is illustrating the small signal equivalent circuit of a MOSFET differential amplifier. So now if you recall, the configuration for the differential amplifier was that we had these two transistors M1 and M2 which were identical and they are matched. So for the biasing we use this constant current source IQ. So IQ is, you can see from here, if you apply the KCL, it's equal to ID1, the drain current of the first MOSFET and MOSFET, and then basically this biasing current is being bifurcated into two branches, ID1 and ID2, and the circuit is symmetrical. The drain resistance are the same RD, and so if you want to this is a single output amplifier. Okay, we are taking the output of the drain from the drain of M2, and you want to drive the AC equivalent circuit, so you go ahead and just kill the sources. For example, the both positive and negative supplies are going to be replaced by the grounds over here. Okay, so you don't have any more the DC sources. Okay, and the current source is going to be replaced by a finite output resistance R0. Okay, so you can see it on the right hand side. So this is the AC equivalent circuit consisting of the small signal models. So the input resistance of the MOSFETs is infinitely high, so we are showing the open circuit conditions here across the signal VGS1. Similarly, the same thing goes at VGS2, and then there's a dependent current source of the transconductance amplifier. GM is the transconductance gain since the transistors are matched, so there's no difference in GMs of both MOSFETs M1 and M2. So with the drain, there's the resistance RD, and then there's again signal ground. Okay, the current source is replaced by R0. So this is the source. Okay, this is the drain terminal, and this is the gate terminal. So the source is tied together, and this is G1, and so let's call this D1, D2, and this is your G2. Okay, so we determine the basic relationships for differential mode gain, common mode gain, common mode rejection ratio from the analysis of small signal equivalent circuit. And figure 6 is showing the small signal equivalent circuit of MOSFET differential pair configuration. So we assume the transistors are matched with lambda equal to 0 for each transistor. Lambda equal to 0 means that you're not considering any output resistance. I mean, if lambda was not 0, then there would have been an output resistance over here, but we're not considering any output resistance. Okay, so there's no output resistance in both the MOSFETs. R0 is infinity. So but that the constant current source is represented by capital R0, that is the output resistance. So the output resistance, you will see that in CMRR, this R0 has a significant contribution. If you want to increase CMRR, which should be ideally, it should be equal to infinity. It should approach to infinity. Then R0 should be very high. Okay, that the resistance appearing at the source terminal should be it should be large. Okay, to have a large common mode rejection ratio. And it turns out that if you don't want to have a finite resistance R0, well, you can replace this by a more sophisticated circuit consisting of MOSFETs, and that active loading might increase this resistance of R0, and you can have a very high common mode rejection ratio. So we are going to discuss that in a while. But anyways, okay, so from this DC circuit, you have the AC equivalent circuit, and you have this small signal equivalent model of the MOSFETs. So all voltages here are being represented by the phasor components. The two transistors are biased at the quiescent currents, and GM1 is equal to GM2, which is GM, right? So the transistors are matched. Okay, so let's start with analysis. If you write the KCL at node Vs, if you consider this node Vs, and you consider these two currents which are coming into the source, the directions are for NMOS MOSFETs, then GM VGS1 plus GM VGS2 is Vs by R0. Okay, R0 is the finite resistance due to the current source, which is biasing the MOSFETs M1 and M2 into saturation region. So from the circuit, we see that VGS1 is V1, which is at the gate G1, minus the voltage at the source node Vs. Okay, so at the source node we had Vs, so that can be written as V1 minus Vs, right? V1 minus Vs over here. Similarly, VGS2 can be written as V2, V2, which is at the gate 2 of the MOSFET 2, V2 minus Vs. Okay, so that's just the difference between the two nodes. So the above equation then becomes, if you replace for VGS1 and VGS2 for V1 minus Vs and V2 minus Vs, this becomes V1 plus V2 minus 2 Vs. Okay, so GM V1 plus V2, then there are 2 Vs minus 2 Vs is equal to Vs over R. So this equation can be written as such. If you are going to expand this for VGS1 and VGS2, you have this relationship. Okay, well, the reasons for you see taking into the picture V1 and V2 here is that we need to derive for the differential gain, and we need the common gain as well, which is in terms of V1 and V2. So we need to have these two gate signals, okay, G1 and G2 for that. Anyways, okay, so solving for Vs, you see, if you make the Vs as the subject of this formulation and rearrange for these terms, you can take this term, for example, over here, you can take this, this will be GM V1 plus V2. So I'm just putting up one more step in between. So this becomes equal to Vs. You take GM in the denominator, on the right hand side of the equation this becomes GMR naught, okay, and then plus 2 Vs. So if you make the Vs, if you're going to make the Vs as the subject of this formulation, Vs is equal to V1 plus V2 divided by 1 over GM R naught, 1 over GM R naught plus 2. Okay, so basically this, you just take Vs out and you will have this expression. So this is the source voltage, this is the AC source voltage that you have at this node. Okay, this node where the constant current source is being applied. So for one side output, for one-sided output of the drain M2, we have V naught is equal to VD2. So you can see this current is, given the direction of the current, you will have a minus sign. Okay, you're taking the output from the drain of M2, so this will be equal to minus GMVGS2 into RD, right? So then we have this minus GMVGS2 RD. You note that this again is in common source configuration, so the output is the difference between the output and the input voltages. There's a 180-degree phase reversal. Okay, so because this is the common source configuration, so that is expected of the direction of the current. Okay, now you can write this as minus GM RD. VGS2 can be written as, in terms of the two node voltages, V2 minus Vs. Okay, V2 minus Vs is your VGS2, and then you can substitute for Vs over from here. You can substitute this Vs over here, and you'll have an expression. If you carry out some algebra and rearrange the terms, well, you will have the output voltage in terms of both V1 and V2, right? And in terms of the transconductance gain of the MOSFET, since GM1 is GM2 is GM, so you have the output voltage. Okay, now you just, based on their relationships between the input voltages V1 and V2, so you just have to rearrange this expression so that it takes the form of V naught equals to AD VD, that is the differential gain that is going to amplify your differential voltage VD, minus plus the common mode gain ACM into the common mode signals VCM. Okay, where, let me define this VCM and VD. VD is not exactly V1 minus V2, but it's written as VCM sorry, V1, it's not okay, let me write this. V1 is VCM, that is the V1 is the voltage at the gate. Okay, so this is the V1 at the voltage at the first MOSFET gate, V1. So V1 is VCM plus VD by 2. Okay, and V2 is VCM minus VD by 2. Common mode voltage, the difference of total, so it will be minus VD by 2. And again, if you see, if you are going to write this as the differential voltage is still being defined as such, so it is still V1 minus V2, difference between the two gate voltages. Okay, you take the difference, this con mode is going to cancel, and you're left with V. That is the differential voltage. Okay, and in terms of this, that's how you are defining your the output voltage in terms of the differential gain and the common mode gain. So you see, based on the relationship between the input output voltages, input voltages are V1 and V2, output voltage is V0. Okay, and we are just expressing that relationship in terms of the differential and common mode voltages, and the above equations can be written as such. Okay, and you can see also over here from these two expressions that VCM is the average of the two applied signals. Okay, so this is V1 plus V2. Okay, you add them up, so you will cancel the differential part of the equations. So your VCM is basically the average of the two gate voltages of MOSFET. All right, so that's your expression. So you see, you have this ADVD minus VCM, and the transconductance gain GM of the MOSFET in terms of the quiescent drain current is twice under root Kn IDQ, which can be written as twice Kn IQ. IQ is the biasing current source. Okay, so there's a difference. IQ is this biasing current source, which has been replaced by a finite resistance R0. If you're going to plug this, so you see over here now, AD is nothing but this part. Okay, this is your AD, and this part is your ACM, the common mode voltage gain. And substituting for GM, you can write this expression as such. You can bring GM over here, so it's 2 under 2 Kn IQ RD by 2. So this can be written in terms of the conduction parameters, the quiescent current, that is biasing the transistors into saturation, and then there's a drain resistor. Okay. Similarly, the common mode gain, if you substitute for GM, is an expression which you can see is in terms of R0. And the very first thing to notice over here is that if you let R0 to be infinitely high, and if the output resistance, the output at the resistance at the source terminal is infinitely high, then ACM is 0. Okay, and this will imply that CMRR, which is AD by ACM, approaches infinity. That is for ideal conditions, but we have a finite output resistance for R0. So we again see that for an ideal current source, the common mode gain is 0, since R0 is infinite. Okay, R0 is infinite because you see over here in the circuit we just replaced this constant current source by R0. But if it was an open circuit or infinitely large resistance, well, then CMRR would have been infinite, right? CMRR would have been very high. Okay, so for infinity or very large resistance open circuit conditions, the common mode voltage gain is 0 for the differential amplifier. But for finite resistance, R0 is to the finite output resistance, you have the common mode gain. So the common mode rejection ratio then becomes the ratio of AD by ACM, and the magnitude of that is found out to be from AD and ACM expressions. You take the ratio, and this is what it is. Okay, so but this again comes in terms of R0. Okay, if you see R0 is very high, then CMRR should approach to infinity. It should be huge. So this demonstrates that CMRR for the MOSFET differential amplifier is a strong function of the output resistance of the constant current source. This example 11.9 shows the dependence of common mode rejection ratio on the R0, the output resistance at the source. So this is the source of the two MOSFETs M1 and M2, which are being biased by the quiescent current IQ, which is being supplied by two transistors M4 and M3. So this in the last video I told you that this also acts as a current source. It's a mirror current mirror circuit, which is responsible in biasing the transistors M1 and M2 without needing of any biasing resistors. This M3 and M4, they drive both the transistors M1 and M2 into saturation by providing the saturation current. Okay, so the objective of this problem is to determine the differential mode voltage gain, common mode voltage gain, and the CMRR of the MOSFET differential amplifier. So you consider a MOSFET differential amplifier with the configuration in figure 3. This is figure 3. We have considered this before in the previous video. So you assume the same transistor parameters as given in example 11.8, except that lambda, the channel width modulation parameter, is not 0, it's 0.01 for AMP4. That means AMP4 is going to have an output resistance R0, which is given by basically we'll have 1 over lambda IQ, so that is 170 kilo. So we have a finite resistance for the current source, right? So for example, 11.8, from example 11.8, we found the bias current was 0.587 milliamps, and the output resistance of the current source now is 170 kilo. So the differential mode gain, just if you look at from this expression, just plug those values for conduction parameters IQ and RD. RD is given as 16 kilos, okay. IQ is 0.587. That is what we had this in the previous example. The substitute value for the values of gain and RD and IQ, you'll find the differential gain as 8.67. Similarly, for common mode gain, use the expression, plug in the values of RD and R0. R0 is the output resistance of the current source, that is the AMP4 transistor, 170 kilos, and this value becomes equal to 0.0469. So the common mode rejection for these values is 45.3 dBs. Now the value of the common mode rejection ratio can be increased by increasing the output resistance of the current source. So an increase in the output resistance can be accomplished by a more sophisticated current source circuit. Figure 7 shows the MOSFET cascode current mirror. Okay, so